Thanks for taking the time to come to this presentation. I'm Nikhil. I work for Airbnb on the ML infrastructure team. So we have been building this thing called Zipline. We recently renamed it to Chronon because of open sourcing protocol and whatnot. So there are a couple of announcements today. So you're in the right place. The talk says Zipline, open source feature engineering framework, but we have renamed it to Chronon, so don't worry. Right. So we are currently doing a private beta. So if you want to be a user or a contributor, please drop a mail. And the slides will be shared online. I'll show a link later. All right. So this is the group of wonderful people that I work with building Chronon. Right. So jumping into the agenda. So we are going to previously, all the talks we have done have been about the technical details of how things work behind the scenes. So this talk is going to be more focused on how to use and set up Chronon at your organization and the requirements that are needed for setting it up. And a short API overview with a few concepts and examples, and a list of dependencies that you would need to set up Chronon, and a brief integration guide. Right. So what is Chronon and how is it differentiated from a bunch of other feature stores that you hear elsewhere? So there are two different terms here, a feature store and a feature framework. So feature store, in my opinion, is something that takes transformed features and manages them for you and serves them for you. Feature framework also includes transforming the raw data into feature data, which is where bulk of the work is. So one of the main goals is we have a uniform API to do all kinds of things, meaning to backfill features from raw data, to create training data, and to serve those features online. Right. And we have a Python and Spark SQL. It's kind of a DSL. This works both online and offline. And most of the definitions that you'll see here will be about converting raw data into training data. Right. And it's the same definition again to go from raw data to feature serving. Right. And beyond this, there is a feature repository that you can use to manage these definitions. So one interesting thing is that this is Python DSL, but it's also compiled. Meaning you would write your Python configurations and run a compile tool that will validate your configurations before you even submit to Spark. So we have made this decision because running Spark jobs takes a while and people want feedback before they begin submitting to Spark. And one other characteristic of this repository is that it's team-based. So companies have teams, and it's quite natural to have this team boundary because team is a good unit of ownership. So if you have a problem with a feature, you can go to the team on-call rotation and bug them. Right. And the last and final goal, in terms of management, is automatic feature monitoring. So because Chronon specializes in backfilling training data, there needs to be a guarantee saying that training data is the same as serving data. So all of that is automatically provided once you set it up. All right. So in terms of API, there isn't a monolithic API. Instead, what we have is a bunch of building blocks. We will go into detail of the building blocks later on. Right? And the idea is that you compose these building blocks to build your features. And one other idea is that most of SQL today is defined for static data, so static relations. But if you're working at a company which is continuously ingesting data, there is different patterns of ingestion into the warehouse. So some data is you're ingesting snapshots of databases every day. Other data is you're ingesting events. There are many kinds of ingestion patterns. And we find it very helpful for users to natively encode these ingestion patterns. We'll see what we mean by source types later on. Right. And this is GroupBy is probably the most powerful primitive that Chronon has. So it, in essence, is an aggregation engine which powers real-time feature computation or midnight accurate feature computation. And it does that both for generating training data and for serving features at very low latency. By low latency, I mean like around 10 milliseconds. All right. And the last native primitive that Chronon offers is join. So we'll see more about what I mean by join, but we are talking mostly about point-in-time correct joins to generate like real-time features, but also backfill them offline. So for serving real-time, as a word makes a lot of sense, but for training, it's not technically real-time, it's like historical real-time. So instead of that, we just call everything point-in-time correct. And the last one is staging query. So users typically require a placeholder to express arbitrary logic. And this is that. So we have split this logic previously from like the other components to have its own place. So people can define their own staging queries. So there is like other properties to how these are all executed. We'll like talk about that later. All right. So in terms of computation, right? Most people, they do what is called log and wait. So if you have a feature definition, you like create an online system which generates that feature online, then you log it. And if you need training data that is worth 180 days, you wait for 180 days to gather that feature and then do training. It's counterintuitive in a sense to do that, because if you can guarantee that this feature is derivable from raw data, and if this raw data already exists in the warehouse, you can backfill it, right? And Zipline helps, or like Chronon helps you do the backfills. Right, and the problem is like most modern models require a huge amount of training data, and that means a lot of date ranges. So if you have that kind of requirement, you're going to do a lot of waiting if you don't backfill. Right, and the other observation is that new features are mostly derived from existing raw data. So we'll like see an example soon, but the next thing with Chronon is that we specialize in doing real-time features. So I think the word itself is self-explanatory, but it is quite critical to have the ability to do real-time feature engineering for various things like recommendations, search, and fraud detection. And it's also one of the hardest systems problem in machine learning. So if you were to put something together, you would need to know how to do stream processing, you need to know how to do batch processing because you need to, if you're looking at lifetime aggregation metrics, like what is the total amount spent by this user on my website across time, you would need to look back into like very, very old data, and that would also require batch processing. Then you need to know how to like store this data so that it's low latency enough for fetching and serving, right? All right, and we'll talk more about backfills, but this is also another very tough problem, especially when it comes to real-time features. All right, non-goals. So Chronon is not a model training or serving framework. You can bring your own model training or serving framework. MLflow is probably like one thing you might be already familiar with, since this is the last day. I'm sure like there's many talks about MLflow. And Chronon is not for interactive exploration. So this is fundamentally due to the engine that we chose, which is Spark, versus something like ClickHouse or Druid, where you can issue queries and get results back in seconds. Spark has this overhead of like allocating executors, waiting for everything to come online, then like producing some data, writing it to Hive, do some very heavy I/O. So the goal of this is, our goal of Chronon is to take a large amount of data, convert that raw data into feature data, and save it into Hive for training, or put it in a key value store for serving. Right, so it's a different kind of usage than interactive exploration, where you have a dashboard, you can like select drop-downs, dimension cuts, etc. So having said that, static usage is fine. If you know ahead of time that this is the kind of dashboard you want to serve, and you're not going to like interactively change the drop-downs, then you can use it for dashboarding too. So going back to the requirements, we are kind of hard-coded to how Airbnb operates today, which is it's based on Kafka and Hive for like event store and like batch data. And we use Spark. We are all at Spark Summit, so I think like this is obvious. So we use that for both batch compute and streaming compute. You can bring your own KV store. There is an API that you need to integrate. We'll like, show it down the line. And to run all of this, we use Airflow, Airbnb, you know. This is the de facto scheduler at Airbnb. But you can bring your own. It's like fairly simple. So what Chronon offers is a template for you to express your Airflow jobs. You can like drop that template into your Airflow repository and begin running that. All right, so let's jump into a simple problem statement, kind of simple problem statement. So we are trying to recommend items for users, and we have this log of timestamps. We know that this user at this timestamp saw an item and purchased it later, right? Now we are trying to, so this is labeled data already, right? I didn't show the purchase in this slide, but the idea is that this is labeled data, and we are trying to enrich it with like new features. So one new feature idea is I want to know what is the view count of this user and of this item in the last 5 hours. And I have this input source, which is a view stream, right? And similarly, I want to know the item rating in the last 90 days. So if you have used Amazon, you know that like having a window on ratings is like quite valuable if you're shopping, because you know products keep changing and they go bad sometimes. So there is a ratings table which has like ratings of an item from a user, and what we are proposing is that a feature which is average rating of this item in the last 90 days from all users is going to be useful. So the problem statement is really simple. We have that, and we have the definitions. What Chronon does for you offline is it's enriching this label data with features. So now this becomes training data. Similarly, online, we are saying that when I ask features for a user, say Alice, at like that particular timestamp, I need to give out those features at very low latency, and the features values should be same between online and offline. Right? This is the very simple high-level problem statement. So just to visualize some of the moving parts here a little bit, so at some point we need a prediction, which is like, should I recommend this item to this user? And at a later point, I know if a purchase has been made based on that view. And I have some data sources. So there is a view data source and a rating data source, and I know that at this point in time, the view count for last 5 hours is 3, and the rating has been 3, right? And at a later point in time, it changes again. The window moves, and then there is new feature values, right? So the right-hand side is the training data set, and at the prediction time also we are serving the same kind of data. All right, so let's break that example down a little bit more. We have the first thing, which is count of item views of a user in the last 5 hours from a view stream. And similarly, the next example. So here, there is different parts to this. So there is aggregation operations, which is count and average. Then there is aggregation inputs, which is item views and ratings. And then there is aggregation key and an aggregation window, which is like last X days or last 5 hours, etc. Right? And then there is data sources. And then there is, so it's implicit here. In this example, we are assuming that it's all real time. But in Chronon, you can choose between daily or real-time accuracy, because sometimes you don't have the streams that are necessary in Kafka. So you can choose between daily or real-time. So let's maybe jump into the data sources. So to understand what I said earlier about different kinds of data sources and modeling that natively in Chronon, we can take like a look at a typical like e-commerce setup where there is a service fleet, there is a production database, right? And then there is warehouse, right? So in the warehouse, there is an event stream that service emits, so clicks, views, purchases, etc. And that becomes an event log. So event streams is something that's in Kafka, some kind of an event store, and event log is some kind of Hive or like Spark catalog. right? And similarly from databases. So this is kind of the new concept here, which is Chronon also ingests change data. So if production database tables gets changed, there is a change capture stream, which becomes a change capture log, right? And then there is also this daily database snapshots. This you might be already familiar with in your organization. So every day there is new sets of data arriving into the warehouse, right? And then there is derived data. So the thing with derived data is like someone else wrote pipelines over this raw data and like did some sophisticated derivations. So you would also like to be able to use those derived data. Even though they won't be like real-time accurate, it's fine. It's still valuable to have access to that derived data. Then there is media. So going back, there is essentially three kinds of data here. There is events, right? Even though they manifest in different environments. Then there is entities. Entities is like things that change over time, but captured as snapshots and change data, right? So if you look closely here, there is really three data sources: the stream, the database snapshot, and the capture log, right? And then there is derived data. So one thing Chronon doesn't explicitly support is operating over media types. That's something we don't do. It's directly related to model training. So generating embeddings from images, for example, is not something you would use like Chronon for example. Right, so let's go back to events. So events is like, let's say, click data or purchase data. So every new partition in the warehouse with a date stamp has events that occur between DS and DS plus 1. Right, so today is 6:30. So if you look at today's partition, it has purchases that happened today, right? And you would have like seen this pattern as like fact source in other analytics contexts, right? And the idea is that this kind of source is enough to do point-in-time correct feature computation, just this table, right? And if you want to go online, you would need a topic with the equivalent things. So there is a click table and a clicks topic. Similarly for entities, this is the ratings table example basically. So there is a ratings table which gets updated, so users can change their ratings, come and update it, like change which will affect the average rating basically, right? So this is based on database table snapshots. People use things like Scoop to move that data from databases into the warehouse. And this is where what we talked about, CDC and mutations come into play. So ratings can change, people can update, change their mind. Yeah, so and this requires an additional mutations table and mutations topic. So it's just that visual that I showed earlier. I'm just like representing them in text here. So in the open source world, the way to manage CDC data is this thing called Debezium over Kafka. So Debezium can be connected to things like MySQL, Oracle, etc., and it can listen to changes and put them in the warehouse for you. All right, so the last one, the way to get PITC here or like real-time features is basically to have the snapshot table and mutation table. And to get the materialized views, you need the snapshot table and mutation topic. Right, so the last kind of source is cumulative source. So cumulative source is a bit special. It's like insert-only tables. Like let's say for some weird reason you wanted to store like clicks in a database table, not as a Kafka stream. That's fine. If you are at low enough scale, the database tables will be able to handle those inserts. So in this case, each new partition is a superset of old partitions. So you can like totally discard the old partition, just look at new partition, and guess what this partition would have been like 4 days ago. You can just like filter out all the new events in the 4 days, right? So it's special, but it enables like for optimization, which is you can like just look at the latest partition and it's enough to backfill features at arbitrary points in time, right? So why do we need all the sources? So we have noticed that not capturing this, so there have been multiple iterations of Chronon or Zipline internally at Airbnb. And we have noticed that defining and capturing these date ranges of sources is very, very error prone. And it's something that people often struggle with, right? Like let's say you want to know 180-day window aggregate of some event data, you need to go back 180 days in terms of partitions, right? For cumulative data, you can just look at the latest partition and it's enough. And for entities, there is some other complex logic, which is snapshot tables, need to go back just one day, and mutation tables are like as of today. Right. So the point of all of this is that not only is it error prone, but these also serve as optimization hints for backfilling. All right. So the next thing is GroupBy. This is probably the most powerful thing that Chronon offers, which is this is an aggregation engine under the hood, and you can access this aggregation engine to compute those features. So the idea is that GroupBy is features derived from same or similar sources. So let's say there is a click source, you could derive multiple features from the same source. And GroupBy is like a group of features derived from that source. Right? And it basically has this notion of a scan. A scan is a from, and a where, and a select. So all three things can be pushed all the way down to the scan query. So if you're familiar with internals of Spark, this all becomes one scan query, right? And then there is keys, obviously, right? And then there is aggregations. So to the aggregations, just like we broke down the example, there is an input operation, then there is a window, which is, so Chronon supports hourly or daily windows. You can set arbitrary number of hours or arbitrary number of days to compute your windows, both for real-time and batch. And then there is bucketing. So bucketing is a bit different in the sense that when you say average, it produces one value for key, right? Now bucketing says you want to produce a map for a user, which is a category to a rating. Like let's say you want to know which category of items to recommend. You want to know what is the rating of this user in various categories. What categories of items do users like? So the core concept from all of this is that aggregations bit again. So there is many kinds of aggregations that Zipline supports. I'm not going to go into detail into all of those, but the idea behind these aggregations is that they're commutative and associative. So they're not order dependent, and they are mergeable. So this is what allows Chronon to backfill them efficiently. So you can break data down into different machines without having to sort them. And you can compute aggregates on different machines and merge them later on. And if you see, there is like a blue and a black coding there. So blue are things that can be reversed. So if there is a delete to a rating or an update to a rating, if you're doing an average or a sum or a count, it's very easy to update the final aggregate without storing all the raw data. Right, so that's the idea. And for the black things, like let's say you're storing just a max, if someone comes and updates that max rating value, you cannot go back. You cannot say, what is the next max, right? You need to keep basically all the data, right? So, and the next bit, which is kind of the differentiator from traditional SQL, is like native window support. So timeline, because we are talking about windows, and then there are events that are happening on this timeline, right? And a query comes in at like 2:27. Right? And we are looking at a 1 hour window. So when you think windows, the first thing that comes to mind is like a sliding window. You're like looking exactly back 1 hour and like aggregating events in the middle. Right? So we are looking at 4, 5, 6. I think this bit is wrong. It should be 4, 5, 6. So the advantage of a sliding window is that it's very fresh. It always has the most recent data. But the problem is it's memory intensive, so as the window moves, you need to pop out the events that are in the back. Right? So you need to store all the event values individually. Right? So, and then there is other kind of window, which is called a hopping window. So same query, which happens at 227. But the hopping window says, you know what, I don't care too much about the query time, but I'm going to store just in 10-minute buckets. And I'm going to give you the aggregation of 6 10-minute buckets. Right? So in this case, we'll have, again, the example is wrong. I think it should be 3, 4, 5. So there are 2 problems with this. So the first problem is that it's stale. It can get as stale as hop size. So if you go back, it's going to return the feature value as of 220, no matter where you ask between 220 and 230. So it's missing most recent data. And it's not ideal for recommendation systems or for fraud detection. Right? But the advantage of this thing is that it's very memory efficient. So you know that there is only 6 hops, and you can store all the aggregates in 6 hops. So in this example, I'm just like showing 3 events, but typically the windows are very large and the events are very dense. There will be probably thousands or millions of events based on your key, and the windows can be as large as 180 days or 360 days. Right, so the point of the graph is that the feature values are going to be stale, and that's not ideal for machine learning. You're losing out basically the information that happened most recently. So what Zipline supports is a bit weird, but it solves both the problems. So it's what's called a Sawtooth window. It is a union of the sliding and the hopping window. It has that feature, which is it captures the most recent data, but at the same time, it doesn't need to keep all the raw events in memory. So the computation itself is scalable. So writes are taken into account immediately, and memory is also bounded. So that's the little bit about like Windows. Right? And the thing with Sawtooth window is that we are varying the window time effectively. So the window size you're saying is 1 hour, but behind the scenes what's happening is that it goes from 1 hour to 1 hour 5 minutes, or like 1 day to 1 day 5 minutes. Right? So the window size can vary, but the idea is that machine learning models like are able to deal with that kind of noise. All right, so join. Join is a much simpler concept than GroupBy. It's basically like you defined a bunch of GroupBys, defined some features, right? And join is basically a collection of all of these features across GroupBys, right? Plus the left-hand side of the join, which is the labeled data typically, right? It's exactly what I said, which is multiple GroupBys are joined together. Yeah, so you can have, so basically most models require a huge number of features, and you can have X number of user feature groups, Y number of item feature groups. There can be like user comma item feature groups. So there can be like any combination of keys here. But the idea is that the left-hand side is timestamped, and we are filling the features as of that timestamp on the right-hand side. Right? And this join is a concept that cuts across both offline and online. So for training data and also for feature serving, this works. So you can say, give me this feature collection which has all these n feature groups, and Chronon would reply with all the features. Right. So let's quickly like jump out of the concepts and like look at the workflow. There is 4 stages. The first stage is explore.py. So you can like, so this is a tool that Chronon comes with. So when you pip install Chronon AI, it will come with this tool, which is explore.py. And you can say explore all pricing features or all user features, etc. And it will give out the list of predefined user features and pricing features. So the idea is that you can begin collecting features without knowing like what a GroupBy does, etc. You just can piggyback on someone else's work and create a feature set that is good enough for a first iteration of a model. Right? So once you explored and figured out what features you need, you author, you like write the join, put all of the features together. Then you compile. This is something we talked about earlier. So compile step is something that validates whatever you wrote very quickly. If there are errors, it will like bubble them up before you have to run and wait for a Spark job. right? And then finally run. This is a thing that's like submits Spark jobs or like fetches data from a key value store, etc. So this is the typical workflow. So you explore, author, compile, and run, and like do this loop until you have satisfactory training data or like serving data. So Explore tool is really simple. You search by a keyword and it will pull out all the group bys or all the feature groups which have this word view or rating in it. All right. And you can also do lineage search of some sort. So you can say, what are all the feature collections that this feature participates in? And also, what are the models that are using this feature? Right. And also, you can search for the data sources for a feature. So it is like a full lineage which goes from data source to the feature name to the model or the feature collection. It also has some information about like who authored this feature and when was it last changed, so that you can like reach out to people if you need to understand a bit more. And the next step is compile. Python is powerful, but one downside is that like it's hard to get that instant feedback of if what you wrote is correct or not without having to run it. So especially when it comes to Spark jobs, running takes a while, and you want to know if what you wrote is correct or not. Right. And another thing with the compile step is that you can see the final representation of your computation, and you can understand the changes that you're making to it. So there can be like complex libraries that you build to like generate group bys or joins. But at the end of the day, it might be hard to reason about what will my change do to the computation. Right. So having this compiled output, which is a JSON basically, and looking at it and saying, okay, I made some change here to the library which generates some 100 joins or whatever. Now I know what exactly the changes to those joins look like. Right. So it makes reasoning about the changes very easy. So the last thing is that this is used to hand off to Scala engine. So Chronon engine is all written in Scala. Users don't have to write Scala, but the engine itself is written in Scala. Right. So, and the last one, so there are many kinds of flows that Chronon supports. I'm not going to go into detail into all of these flows, but you can use any of these flows flexibly by defining those configs I talked about earlier. Right. So this is like the rough serving architecture. Right. So there is a feature declaration, then there is like streaming data, then there is batch data which goes into a feature store, and then there is a model server, and then there is a feature client. Right, so all of this needs to run regularly, and we use Airflow to drive this whole flow. Airflow and Spark, basically. So we're submitting Spark jobs through Airflow workers. Right. Yeah, so in terms of repo, it's like split by the concepts that we described earlier, basically, and each team has its own folder. So it's very clear, like if you're using someone else's features, or someone else's feature collections, etc. Right, and then there is teams.json where like each team can configure how their jobs run or how their data is consumed or produced. Right. Yeah, so one important detail about Chronon is that, so if you have used Airflow, each day has a task typically, and each task represents the production of data for that day. So this is where Chronon differs in the sense that no matter when you run it, it's going to fill in all the data that has been left empty. So let's say the last time you ran something was like last month, and you're trying to run something today. We're going to fill in the 30 days worth of gap for you in that single task. So we do that for two reasons. One is that this is the typical workflow for machine learning. You're backfilling feature data very often. And the other reason is that we reuse compute. So if you are computing 30 days worth of features, we reuse all the intermediate compute. So the jobs are much faster than like running one day at a time. All right, so online, our goal is to serve all the features in low latency, and our target is to be around 10 milliseconds. Obviously, this varies by the feature collection, right? And also serve this at high QPS. So internally, we use a variant of Hashbase, but I'm sure like any other key value store that you have outside will have similar performance. Yeah, so last note is about online integration, which basically is integrating with the KV store and integrating with the streaming system. So this is something that someone does one time, and like the entire company can like build on top of this. Yeah, I'll just like stop there and like leave some time for questions. Again, thank you for listening.
Awesome. So we're actually out of time for live questions, but if anyone has questions for Nikhil, please come to the stage. Thank you very much.